Okay, let's go to the next topic, the electric circuits. To begin with, let's define current, the electric current. Imagine that we have a wire and we have current, that's the symbol for current, and we take one point as a reference, this point, and we can count, for example, how much charge is causing this reference point per second. And that's the definition for current. Current is defined as the charge, that's the symbol for charge, Q, correct, divided by the time, right? How much charge per unit time is causing this reference point. And that's current. Actually, it says the average current because the time is long time, so the current is average current. Great. It's a new quantity, so it has a unit. The unit is called amps or ampere. The unit for current is amp or ampere, symbol A, right? So 1 amp is equals to 1 coulomb per 1 second, coulomb per second, right? Okay, now when we're dealing with current, we have two types of current. We have direct current, DC, and we have alternating current, right, AC. Direct current is when the current takes on, or the charges in this case, takes only one path all the time, right? Only one path. Only current, right, or charges, correct, take only one path all the time. One path, correct, all the time. The best example is the battery. Right, the battery. For alternating current, the current is oscillating. It's changing a direction, right? It moves back and forth. That's why it's alternating. So it changes direction all the time. Changes direction, right, all the time. Okay, and the best example is that generator. That's the best example. The light that you have at home, right? That's alternating current is produced by a generator. Great. Now, when we're dealing with a circuit means actually a circle, how to create circles with some elements, right? So we have, for example, in direct current using the battery. This is the symbol for battery, right? And imagine we have a switch right here. And imagine that we have a light bulb. Correct, imagine. Okay, and this is positive and this is negative. Positive and negative. Look, if the battery is not connected to the circuit, we call this the electromotive force. Right? This is called electromotive force, or EMF. Right? But when we close the switch and produce the circuit, the circle, right? Now the electromotive force changes usually, right? Because in this case the battery is part of the circuit when we close the circuit. And what happens? Well, we just take this as the potential difference, right? So electromotive force and potential difference, the same meaning. Electromotive force is the ideal case, no resistance in the battery. If we have some resistance, we call it, right, voltage. The same idea, the same meaning. Okay, perfect. Now, let's go to Ohm's law. Ohm's law. Remember, the charges that moves by convention is the positive charge, right? The charge that moves is the positive charge, so we have current in that direction. By convention. Okay, great. Now let's go to Ohm's law. So we're dealing with voltage. We explain the idea of voltage using the idea of pressure. We know that if we have pressure, we have these two containers, right? And this has this pressure, right? And it has this pressure, correct? And now we connect these two with a bulb right here. Imagine. When we use the idea of pressure, pressure is equals to density GH. H is the depth, right? H1, right? Maybe H2. Because right here, the pressure is more than right here, we have current from here to here, correct? Okay, the same thing happens when we have electric potential. When we have electric potential, imagine this is the same idea. Okay, imagine this is electric potential equals to 20 volts. The electric potential, this is case 1, case 2, gonna be 10 volts. Or imagine. What happens when we connect these two with a wire? Well, we have current, correct? Perfect. Now, what happens after a while? Right here. Well, after a while, we have current from the left container to the right container, and later they get the same level. When they get the same level, they have the same pressure in both sides. If they have the same pressure, there is no more current. So they are in equilibrium. The same thing happens right here. Right? We have current from here to here, but later, after a while, these two have the same electric potential, and there is no more current. Stops the current. Correct? Perfect. Now what happens if we increase? If we increase the pressure, well, we increase the current. Right here. The same thing happens right here. What happens if we increase this difference? Okay, this one right here. Well, we increase the current right here. How we represent this concept? Well, in this way. We say that the current is proportional to the voltage. Correct? If we increase the voltage, actually we can call the voltage is represented. I remember when we're dealing with voltage, we use this symbol, voltage potential difference, or we can use this symbol. The meaning is the same. Okay, so it's proportional to the voltage. Also, what happens if we increase the resistance? If we increase the friction right here, imagine that we have this situation, correct? But now let's increase the friction. If we increase the friction through this pipe, right, that current decreases. The same thing happens right here. Imagine that we change out this wire by another wire that has more resistance, then the current decreases. Means what? We could present that idea in this way. Current is inversely proportional to the resistance. Correct? Perfect. Now let's combine these two concepts. Remember, these are factors that act on the current. So the factors multiply. So how do we have? Current is proportional to voltage over the resistance. Alright? How do we eliminate this symbol? Using a constant. So current is equals to a constant voltage divided by the resistance. But because this is the unit for current and the resistance, correct? We take K2B equals 1. So in this case, current is equals to voltage divided by the resistance, right? Or we can say that voltage is equals to current times resistance. This is Ohm's law. Ohm's law. Voltage is equals to current times resistance. The unit for resistance is called ohms, right? Unit of resistance is ohm, and the symbol is omega. Right? The units, remember the units for voltage is volt, for current is amps, and for resistance is gonna be ohms. Correct? Also, ohms found that the current, actually the resistance, is coming in this way too. Look, you have a wire, this wire, imagine, if we increase the length, this is initial, this is, let's say, final length. Well, we're here, these two are the same material, correct? This has some resistance 1, this has some resistance 2. If we increase the length, we increase the resistance. So the resistance is proportional to the length of the wire. Also, if we have this thickness of the wire, correct? If we increase the thickness or cross-sectional area, this is area, right? Area 1, area 2, it's found that the resistance decreases. So in this case, we have the resistance is inversely proportional to the area, correct? This is why temperature is constant. Perfect. Now, when we combine these two concepts, what do we have? The same thing as in this case. We have that the resistance is proportional to the length divided by the area. Let's eliminate this symbol, right? And we have to use a constant, like right here. But in this particular case, the resistance is equals to this quantity that depends on the material. This is called the resistivity of the material times L over area. So the resistance equals to resistivity, length divided by the area. Again, this depends on the material. Could be gold, could be silver, aluminum, copper, and so on. Okay, perfect. Now let's go to power, electric power. How do we define the electric power? Let's do it. Let's find a formula that give us that electric power. Let's do it. How do we define power? Remember, in mechanics, power is defined as work or energy divided by the time. But how do we define work? Remember, a potential difference. This is changing time, right? Potential difference, but that is equals to work divided by the unit charge. From here, we have that work is equals to charge times potential difference. Let's substitute this value right here, and what do we have? This is equals to charge, correct? We define first current. Remember, current is equals to charge divided by the time. And then what do we have right here? We have this charge times voltage, correct? Divided by delta T. But what is this quantity? That is just current, correct? So power, the electric power is just equals to current times the voltage, or potential difference right here, correct? Perfect. So electric power is equals to current times voltage, or voltage times current. Great, and it's a new quantity. Also remember that every time we have a quantity multiplied by another quantity, we create a new quantity and we have to define it. And we define it as power, right? Electric power. Electric power. Then what is the unit for power? The same thing as in mechanics. Unit is watt. Okay, unit watt. Correct? Watt. Perfect. Also, this is the average power. Okay. Also, we can use the Ohm's law right here. We can use the Ohm's law. What do we have? If we use voltage right here, so this is equals to current times voltage, but voltage is current times resistance, correct? And this is equals to current squared times resistance. Also, we can use this quantity right here, right? Current squared times voltage. Also, we can solve for current, correct, and plug it right here, and we create another equation. They are the same at the end. Okay, perfect. Now let's go to circuits in series and in parallel. Great. When we're dealing with circuits at this level, right, we mentioned two types of circuits: circuits in series and circuits in parallel. Okay, types of circuits. Okay, we have two types, right? In series and in parallel. When we're dealing with circuits in series, in this case, current takes only one path. Right? Current takes one path. And voltage is the sum of the voltage drops. Right? Voltage is the sum or total of the voltage drops. What about in parallel? In parallel, current is split into two or more paths. Current, in this case, also current is constant. Okay. What about in parallel? This is the opposite. In this case, current split into two or more paths. And right here, voltage is constant. It's constant. Okay, let me go and explain circuits in series. We have this part. Before going to this, before going to explain this, it's better to go to the circuits element. Okay, circuits elements. These are the circuits elements. We have the resistor, right? We can use this symbol, or we can use this symbol too, right? Or that's the resistor. We have also the capacitor, right? That's the symbol for capacitor, right? Capacitance. Also, we have the inductor, right? That's the inductor. And then we have the voltage source, right? Voltage source. Perfect. Look, the function for a resistor is to dissipate energy. The function for a capacitor is to store charges and electric energy. The function for the inductor is to store the magnetic field and magnetic energy. And the voltage source, well, we have at this level two sources, which is the battery and the generator. Okay, perfect. So we have again these elements that are used right on these circuits. In series and in parallel, we can use just resistors, we can use just capacitors, we can use just inductors, or we combine them, right? Resistors and capacitors, resistors and inductors, right? And so on. Okay, perfect. Now let me explain these two types of circuit, in series and in parallel. Great. So in series, for the moment, let's work only with resistances, right? We mentioned that we have resistors, circuits using only resistors, and then we have circuits using only capacitors, right? And so on. Okay, let's go only for resistors. And then let's use the battery, and these are the resistors. Imagine that we have three resistors for simplicity. This is R1, resistor 1, resistor 2, correct, resistor 3. And we have the current by convention, goes from positive to negative charge, correct? It's our voltage, volt. Okay, according to this, it says that in series, the current takes only one path, okay? There's only one path taken by the current, or along this circuit. Okay, now let's say it says voltage is the sum of the voltage drop. Look, when we take into account this resistor, through this resistor we have a current. When we multiply the current and the resistance, we create voltage, right? Current and resistance, and we call that voltage drop. This one. This we call it V1. The same thing happens right here, right? In this direction we have the current, and that's the current. And the same thing. The current is constant, correct? And then what do we have? This is voltage drop 2. Another voltage drop right here, right? 3. So what should be then voltage? Voltage, the total voltage is equals to V1 plus V2 plus V3. Correct? Perfect. Now, how do we define again voltage? Using, not define it, but let's use Ohm's law. Ohm's law, which is current times resistance. So it's equals to current times resistor 1 plus current resistor 2 plus current resistor 3. But look, the current is constant, so we can factor it out. And what do we have? This is equals to current times resistor 1, resistor 2 plus resistor 3. Correct? And when we compare this to a Ohm's law, right? The Ohm's law formula, we say that the total voltage is equals to the total current times the total resistance. In this analysis, we call this the equivalent resistance on this equation right here. Correct? So it's going to be voltage times the current times the equivalent resistance. But the equivalent resistance for circuits in series is going to be this one. When we compare this form, right, pound, and the general form for Ohm's law, we can see that the equivalent resistance is just the sum of the resistances for circuits in series. Okay, so we have then that this is the equivalent resistance. We can also call it like this, right? Equivalent resistance in series is equals to R1 plus R2 plus R3. Perfect. Now let's go to circuits in parallel. Okay, let's do it. Circuits in parallel. For circuits in parallel, this is the classical one. We have the voltage, we have resistor 1, resistor 2, resistor 3. Okay, this is R1, R2, R3. When we have current, this is total current is split by these three paths. This is current 1, right? Current 2, and current 3. And this is the voltage, right? The voltage, we mentioned that is constant when this circuit is in parallel, correct? But what about the current? The total current is equals to current 1 plus current 2 plus current 3, right? This is conservation of the charge, correct? And in this case, we have the conservation of energy. Conservation of energy, conservation of the charge. Okay, perfect. And what do we have? How do we? Let's use again Ohm's law as we did before. Ohm's law. And what do we have? This is voltage 1 over resistor 1 plus V2 over R2 plus V3 over R3. Correct? But how is the voltage? The voltage is constant. So the V1 is equals to V2 equals to V3. So what do we have? This is the total. Is equals to the total times what? 1 over R1 plus 1 over R2 plus 1 over R3. One more time, when we compare this to Ohm's law, current equals to voltage over resistance, right? We can see that 1 over the resistance, again we can call it the equivalent resistance, is equals to 1 over R1 plus 1 over R2 plus 1 over R3. Correct? And this is in parallel. 1 over R1 plus 1 over R2 plus 1 over R3. Of course, we were looking for the total in parallel is equals to 1 over R1 plus 1 over R2 plus 1 over R3 inverse. It's one way we can do it, how we can do this. Correct. Perfect. And these are the resistances of the circuits when we have in series and in parallel. These two conclusions. The rest are we use Ohm's law. Correct. Perfect. Now, when we're dealing with parallel circuits, also we can represent that circuits in different ways. We can use this way, or we can use this way for parallel. Right? Imagine this is for parallel, positive and negative. We can use this one this way. This is resistor 1, or we can use this one, resistor 2, in this way, and finally resistor 3 correct in that way. And you can see all of them have the same voltage, and this is R1, R2, and R3. Or another way should be this one. Okay, we have the total current split by 3 paths. This is 1, 2, and 3, for example, correct? And imagine this is the battery right here. This is R1, this is R2, this is R3. These three are the same. This, and this are the same. Okay, so it gets in parallel. This is the total current, correct? This is current 1, this is current 2, and this is current 3. The same thing as in this case. Correct? Okay, let's stop right here this analysis of electric circuit. We conclude this in the second video, right? Electric circuit. Great. See you in the next video. Bye.